Improving the multi-step reasoning of language models depends on a technique called reinforcement learning with verifiable rewards, or RLVR. The model generates a chain of logic, and an algorithm scores it against a known verifiable answer. Currently, the lack of high-quality, verifiable training data is stalling the process. Human experts are slow and expensive to scale. Alternatively, using frontier models to generate synthetic reasoning traces is costly and prone to hallucinations, introducing errors into the verification process RLVR relies on. Researchers from Cornell and Cambridge investigated an alternative: rule-generated synthetic data. Instead of mining human text or prompting LLMs, they used context-free grammars and logic programs to generate training samples automatically. These procedural generators build entirely fictional universes. A dataset like PhantomWiki creates family trees for non-existent people, while GSM Infinite constructs random arithmetic graphs. Because the underlying logic is procedural, every question comes with a mathematically guaranteed ground truth. A synthetic question asks, "Who is the nephew of the friend of the person who likes birdwatching?" Contrast this with a multi-hop question from HotpotQA, which combines Wikipedia paragraphs to find a historical fact. Synthetic sets contain no factual information relevant to reality. This raises a central research question. Can a language model develop general reasoning capabilities by training exclusively on fictional, semantically simple logic? To test this, the team applied RL fine-tuning to models between 0.6 and 4 billion parameters. They used the group relative policy optimization algorithm, training the models solely on these fictional synthetic datasets. These charts establish baseline performance. Dashed lines indicate pre-training accuracy on HotpotQA, 2Wiki, and Musique. After RL fine-tuning on fictional worlds, accuracy surges above baselines. Qwen 3-0.6b shows up to a 131% improvement on HotpotQA. These gains are consistent across models. The models are succeeding at real-world fact retrieval by using logic patterns learned from fictional entities. The results indicate that knowledge composition, the mechanical skill of chaining information across steps, transfers from fictional environments to tasks with high semantic complexity. A common critique of RL fine-tuning is that the model might only learn to reward hack, improving its score by mastering the required output format, like putting answers inside specific tags, rather than improving its reasoning. To isolate this effect, researchers conducted an ablation study. They trained the models with a reward given only for correct formatting, with no reward for the actual accuracy of the answer. In Qwen 2.5-1.5b, format training alone increased the score to 0.43. This confirms initial gains are often just learning output structure. However, Qwen 3 and 5.4 score stayed flat. They already had perfect formatting, so syntax rewards provided no improvement. Because format training did not improve these models, the gains they achieved through synthetic RL must be attributed to the underlying logic used to arrive at the answer. The data suggests that for these models, the transfer is algorithmic. They are refining the internal mechanics of the reasoning process itself. Another possibility is that RL fine-tuning is simply surfacing Wikipedia facts the model memorized during its pre-training phase.
If the model already knows the answer from its training data, RL might just be teaching it how to retrieve it. To test for true generalization, the researchers evaluated the models on held-out PhantomWiki universes. These contain entirely new fictional facts that the model has never encountered in any previous training phase. The training data only covered questions requiring between 1 and 9 logical hops. When tested on out-of-domain difficulties, like questions requiring 14 hops, the models remained accurate, successfully processing complexity levels entirely absent from their training. Extrapolating to these higher difficulties suggests the model has bootstrapped a general chaining algorithm rather than just memorizing specific solution patterns or templates. This isolation confirms that the models have acquired knowledge composition as a domain-independent skill, refining the process of integrating information regardless of the factual domain. We can also compare RL fine-tuning to supervised fine-tuning, or SFT, where the model is given the correct reasoning trace to imitate directly. On synthetic math data, SFT improves the model's accuracy on the training task, but that improvement fails to transfer to the real-world HotpotQA benchmark, where the SFT model shows almost no gain compared to the RL-trained model. SFT tends to overfit to the linguistic templates of the synthetic data. In contrast, the outcome-only reward of RLVR forces the model to develop its own internal mechanics for arriving at the correct answer. This positions RLVR as the primary method for eliciting reasoning skills that can generalize beyond a specific training environment. Since RL fine-tuning only rewards the final answer, we need to know if the internal reasoning process is actually improving, or if the model is finding shortcuts to the right output. By looking at the model's reasoning traces on MusicQA and counterfactual QA, we can verify if the intermediate facts it generates are correct. Over 5,000 training steps, the proportion of correct intermediate answers increases. Even though only the final answer was rewarded, the model's thinking process became more grounded. Demanding a verifiable final answer from a complex logic graph appears to create a byproduct of process-level rigor. This emergent accuracy in the intermediate steps confirms that the model is performing genuine multi-step reasoning to reach its conclusion. These results point to a clear scaling trend. Real-world performance growth is monotonic as a function of the number of synthetic training samples the model processes. Unlike human annotated data, where overfitting is a common risk, these models continue to improve across thousands of steps of synthetic RL. Rule-generated synthetic data provides a scalable vector for increasing performance without the constraints of human-labeled datasets. It is effectively infinite and fully verifiable. By training models on the abstract rules of fictional universes, they develop the structural skills needed for linking information in the real world. Evidence indicates that the core mechanics of knowledge composition can be refined using fictional environments alone, allowing models to solve real-world complexities through purely logical practice.